Hi everyone, and welcome back to another episode of Dr. Kyle Explains, your YouTube channel where we go through GCSE science content quickly and easily. Today we're going to be going through the pH scale and strong and weak acids. So without further ado, let's grab a pen, grab a paper, and let's go ahead and jump in. Okay, so some key content as always, first of all. So acids produce the H+ ions in aqueous solutions. Aqueous solutions of alkalis produce the hydroxide ions, minus OH ions. In a neutralisation reaction, the H+ ion and the minus OH ion react to form H2O. So you literally have H+ plus minus OH goes to H2O like that. There's your acid, there's your alkali, you neutralise it to make water. Now, just to remind you, the state symbols again, S are solid, L is liquid, G is gas, and AQ is aqueous, and that means dissolved in water. So you often find you have AQ written there, AQ written there to show it's dissolved in water, and then that will be a liquid there for the water. Okay, so the pH scale then. So the pH scale runs from 0 to 14 just along here. And so from 0 to 6 we have an acid, and then from 8 to 14 we have an alkali. Sometimes this is known as the basic side. So in the middle we have 7, this is neutral. And then from about 0 to around about 3 is a strong acid, so that's lots of hydrogen ions. And then from about 4 to 6 is a weak acid. And then from about 8 to around about 10 is a weak alkali. And then from 11 to 14 is a strong alkali. Now, for your GCSE, you do need to know all of this and the sections of it. And you also need to know that universal indicator is an indicator that is used to determine, or give an indication at least, whether something is an acid or an alkali. Now, in universal indicator, acids will turn red, kind of from orange to yellow. So yellow meaning kind of a weak acid, red meaning a stronger acid, orange in the middle. Neutral is 7, so that's green. And then an alkali runs from kind of blue all the way up to purple. And again, purple is a strong one. Blue is kind of your weaker alkali. Now, people often get this muddled up. A lot of this seems to be generally common knowledge. You kind of learn often about this in year 7 and 8. But you need to realise this is only in universal indicator. So the pH scale runs from 0 to 14 regardless. You can have an acid that is pH 1. That does not mean that it will be red. It will only be red if you add a universal indicator to it. If you add a different indicator to it, something like, say, phenolphthalein, it might change colour, but it's not going to give these kind of colours. Phenolphthalein is a pink indicator only. It will only turn pink, and that's it. So it will only turn these colours when universal indicator is added. Now, universal indicator can be a liquid, or it can be a piece of paper that you put in. It will change the colour, but again, it's only when there is universal indicator present. So another way of looking at this is using a pH probe. Now, a pH probe is essentially a kind of a very small machine. It's this black kind of wand here, and you link it up to a digital display, and it will tell you what the pH is. Now, the advantage of this is they're far more accurate. So rather than looking at kind of a colour and going, oh, is that orange or is it red? I'm not really sure. It will just tell you what number it is. It also has better resolution. So that means rather than just kind of going, again, what colour it is and then going, oh, I think that's orange, so it's about 3, it will tell you it's 3.2. So that's much better resolution for finding that out. They're relatively easy to use because you just stick it in and it will tell you the number, and there's no contamination. So when you add universal indicator to your sample, you are contaminating that sample then with universal indicator. You have to get rid of it. Disadvantage of a pH probe, however, is you have to calibrate them before use. So they tend to be slightly longer. They take longer to use. And obviously, because it's a machine, it's more expensive than the chemical indicators. Okay, so the ionic equation for neutralisation is H+. So that's coming from your acid. Your OH-, that's coming from your alkali. And then your water is being formed from that. So hopefully we can see H, 1 hydrogen, 1 oxygen, 2 hydrogens, H2O. That's where it's coming from. So in a neutralisation reaction, the hydrogen ions react with hydroxide ions to form water. So if we take an example then, if we did NaOH plus HCl, here, which we've done before, this is a metal hydroxide. And here we've got an acid, a strong acid. And so what's that going to make? It's going to make a salt plus water. And it will neutralise it because you've got your hydroxide there and your hydrogen. So you're going to make H2O. And then what's left over is NaCl. Really well done if you followed that through. Just going to double check it's all balanced. So 1 sodium, 1 sodium, 1 chlorine, 1 chlorine. 2 hydrogens and an oxygen. Yeah, lovely. Done. So just as an example, that's the ionic equation for neutralisation, which you do need to learn for your GCSE. And then that's just an example of how it's forming the salt and the water in a chemical reaction. Okay, so strong versus weak acids. Now this is higher tier only stuff. So if you're not doing the high tier, you can stop now. But I just want to go over exactly what the difference is between a strong and a weak acid. So for a given concentration of aqueous solutions, remember aqueous means dissolved in water, the stronger the acid, the lower the pH. So the further you go down the pH scale, so the difference between a pH of 3 and a pH of 1, pH 1 is the stronger acid. So a strong acid, the H plus ion, is completely ionized when dissolved in water. Now you do need to learn that definition. So a strong acid, the H plus ion, is completely ionized or fully ionized when dissolved in water. A weak acid, the H plus ion, is only partially ionized when dissolved in water. So what does that mean? So I always tell my class to kind of divide their page into, so I'm going to put strong here and I'm going to put weak over here. And then I'm going to have 5 HCl's. Okay, so HCl is a strong acid. And then I'm going to have 5 H2CO3. Now that's carbonic acid. That's a 3 there, sorry. Looks a little bit like a 5, 3. Okay, so then what we're going to do is we're going to just draw a little tank here. Not a very good tank, but a tank nonetheless. And it's full of water. Because remember, you have to dissolve it in water for that H plus ion to become acidic. Dissolve it in water. So we're going to dissolve these in water. Now, a strong acid is completely ionized. And so what that means is all of those hydrogens there from the 5 HCl, we are going to end up with 5 H pluses floating around in solution. 1, 2, 3, 4, 5. They are going to be completely ionized. Now, obviously, the Cl minuses are still going to be floating around. But now those ions are free to move in solution. 1, 2, 3, 4. Those ions are free to move in solution, and the acid is completely ionized. Whereas a weak acid, so it's still an acid, so you've got your H plus, and you've got your HCO3 minus, this is carbonic acid, but the rest of them are still going to be H2CO3s. So what this means is even though the concentrations are the same, 1, 2, 3, 4, 1. So there's 5 in here and 5 in here. In the terms of the weak acid, it is only partially ionized. Most of the acids are still H2CO3, whereas we have 1 H plus floating around, and that is what makes it acidic. So because we've only got 1 hydrogen ion floating around, it is a weak acid. So even though the concentration is the same, we've got 5 and 5. Here, if you dissolve it in water, it will be fully ionized. Whereas in this one, you only have 1 hydrogen ion, and so it is a much weaker acid. And so that means it will be further up in the pH scale. Okay then, so pH number. So as the pH of the solution decreases by 1 unit, the hydrogen ion concentration increases by a factor of 10. So what does that mean? So essentially, if you take a pH of 1, it will have a concentration of 0.1 moles per decimeter cubed in solution. And so you could write that as 1 times 10 to the minus 1. Now, that also means pH 2 has a 0.01 mole per decimeter cubed solution. And so that is 1 times 10 to the minus 2. And so all you do is you keep going here. And so you would take, for example, 1 times 10 to the minus 6. And so that would give a pH of 6. And so all you do is you take this number at the top here, and that tells you the pH. So in terms of the alkaline numbers here, if we had 1 times 10 to the minus 14, it would have a pH of 14. And so in terms to find what the pH number is, you just take the power of the hydrogen ion concentration, and that will tell you the pH number. And so what we need to recognize is every single time you decrease the number, it is getting stronger by a factor of 10. So pH 14, 13 is stronger by a factor of 10, 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 all the way down until eventually you get to pH of 1. And so that essentially means if you have an acid at pH 3, that's a factor of 10, a factor of 10. So a pH of 1 is 100 times stronger as an acid. So hopefully you followed that through. The key message here is whatever the number is at the top, that's the pH. So if it's minus 2, it's a pH of 2. If it's minus 1, it's a pH of 1. Okay, so what have we done today then? We've described what neutralisation reaction is and what's produced. We've described what ion makes solutions acidic or alkaline. We've written ionic equations for neutralizations. We've described what the pH scale measures. We've described how an acid can be strong or weak, and we explained the difference between the concentration and strong or weak acid. Haven't planned the investigation today, but we will do that in another video. And we've described how the concentration of hydrogen ions relates to the pH number. Thank you very much for watching. Please do go through more of my videos for more GCSE science help. And remember, if you ever need any help, Dr. Kyle explains.